Let yourself settle in. Find that spot where your body can truly relax, where the weight of the day begins to drift away like morning mist dissolving in sunlight. Take a slow, deep breath, feeling the air fill your lungs, and as you exhale, let any lingering tension flow out of you. Tonight, we're embarking on a journey to one of the strangest places in the entire universe, a place so empty, so vast, that it challenges everything we think we know about cosmic structure and the very fabric of space itself. We're going to explore cosmic voids, enormous regions of space that are almost entirely empty. But these aren't just empty spaces, they're cosmic mysteries that hold clues to the deepest questions in cosmology. So close your eyes if you'd like, or let them rest gently on a distant point, and allow this story to wash over you like gentle waves on a quiet shore. Don't worry about remembering every detail or understanding every number. Just let the cosmic landscape unfold in your mind, painting pictures of vast emptiness that somehow shapes everything around it. Before we drift into the cosmos, if you enjoy these journeys through space and science, please take a moment to like this video and subscribe to the Science Pillow. Your support helps us continue creating these peaceful explorations of the universe, blending curiosity with calm, education with relaxation. And now, let's venture together into the greatest emptiness in existence, where nothing about these cosmic holes is normal, the discovery of the great nothing. On an ordinary evening in 1981, an astronomer named Robert Kirshner sat in his office at the University of Michigan, studying data that would fundamentally change our understanding of the universe's structure. Kirshner and his team weren't looking for anything particularly extraordinary. They were conducting what seemed like routine work, a survey of galaxy redshifts designed to create a three-dimensional map of the cosmos. Redshift, for those unfamiliar with the term, is the phenomenon where light from distant objects shifts toward longer, redder wavelengths as those objects move away from us. It's a cosmic measuring stick that allows astronomers to determine how far away galaxies are and how fast they're receding due to the expansion of the universe. The survey involved pointing telescopes at different patches of the sky, measuring the spectra of galaxies in each region, and calculating their distances based on how much their light had been redshifted. It was methodical work, the kind of careful observation that forms the backbone of astronomy. But as Kirshner and his colleagues analyzed their data from a region near the constellation Boötes, they noticed something that made them pause and double-check their calculations. In this particular direction of the sky, there was almost nothing. Not just fewer galaxies than expected, almost no galaxies at all. At first, they suspected an error. Perhaps their instruments had malfunctioned. Perhaps they'd accidentally pointed their telescopes at a region obscured by dust or gas. But repeated observations confirmed what seemed impossible. They were looking at a vast region of space, hundreds of millions of light-years across, that contained only a handful of galaxies. Where they should have found approximately 2,000 galaxies based on the density of galaxies elsewhere in the universe, they found fewer than 60. The discovery sent ripples through the astronomical community. Kirshner and his team had stumbled upon what would come to be known as the Boötes Void, sometimes called the Great Nothing. It was one of the first large cosmic voids ever detected, and it remains one of the largest and most dramatic examples of these empty regions in the observable universe. The Boötes Void sits approximately 700 million light-years away from Earth. To put that distance in perspective, Light traveling at 186,000 miles per second takes 700 million years to traverse that gulf. When the light we now see from that region began its journey toward us, Earth was a vastly different place. Complex life was just beginning to flourish in the oceans. The supercontinent that would eventually break apart into the continents we know today was still forming. The void itself spans about 330 million light-years in diameter. Imagine lining up more than 300 Milky Way galaxies end to end. That's the scale we're discussing. It occupies roughly 0.27% of the diameter of the entire observable universe. That might sound small, but in absolute terms, it's incomprehensibly vast. The void is so large that if you could somehow travel at the speed of light, it would take you 165 million years to cross from one side to the other. What makes the Boötes Void so striking isn't just its size, but its emptiness. The 60 or so galaxies that have been detected within it aren't randomly scattered throughout its volume. Instead, they cluster along a tube-like structure that runs through the middle of the void, like beads on a cosmic string. This suggests that the void might have formed from the merger of several smaller voids, with this central filament representing the last remnants of matter that haven't yet been pulled away to the void's edges. The discovery was serendipitous in many ways. If Kirshner's team had been conducting their survey just a few degrees in a different direction, they might have missed the void entirely. But once they found it, astronomers realized that this great nothing was trying to tell them something fundamental about how the universe is structured. In the years following the discovery, astronomers began to understand that the Boötes Void wasn't unique. Other surveys revealed more voids, smaller and larger, scattered throughout the cosmos. The universe, it turned out, wasn't a smooth distribution of galaxies uniformly spread through space. Instead, it had structure on the grandest scales imaginable, a cosmic web of filaments and walls surrounding enormous empty regions. The voids weren't anomalies. They were fundamental features of the universe's architecture. Kirshner himself reflected on the discovery with characteristic scientific wonder tinged with amazement. He noted that if our Milky Way galaxy had formed in the center of the Boötes Void, instead of in the relatively crowded region of space where it actually resides, we wouldn't have discovered other galaxies until the 1960s. Our entire understanding of the cosmos would have been delayed by decades. The universe would have seemed far lonelier, far emptier than it actually is. We would have looked out into the night sky and seen almost nothing but darkness. That thought experiment highlights just how unusual and dramatic these voids are. They represent a kind of cosmic isolation so extreme that it challenges our intuitions about space and structure, and, as we'll explore, they're not truly empty. They contain mysteries and phenomena that continue to puzzle astronomers and cosmologists to this day. Understanding cosmic voids, the architecture of emptiness. To truly appreciate what cosmic voids are and why they're so important, we need to zoom out and look at the large-scale structure of the universe. When astronomers create maps of galaxy distribution across billions of light-years of space, they don't see a random scattering of points like stars against a dark sky. Instead, they see something that resembles a three-dimensional spider's web, or perhaps more accurately, a vast cosmic foam. Galaxies aren't distributed uniformly through space. They cluster together, forming groups and clusters that contain hundreds or thousands of galaxies bound together by gravity. These clusters themselves string along elongated structures called filaments, which can stretch for hundreds of millions of light years. The filaments connect at nodes, dense regions where multiple filaments intersect, creating the most massive concentrations of matter in the universe. Between these filaments lie the voids, enormous bubbles of space that contain very few galaxies. This structure, known as the cosmic web, is one of the most fundamental organizational principles of the universe. It exists on a scale so vast that it encompasses everything from individual galaxies to the largest structures known to exist. And, crucially, the voids are not minor features of this web. They dominate it. Cosmic voids occupy approximately 80% of the volume of the universe. That means that most of space, by volume, consists of these underdense regions. The galaxies we see, including our own Milky Way, exist in the dense filaments that make up only about 20% of cosmic volume. So, how did this remarkable structure come to be? The story begins in the very first moments after the Big Bang, 13.8 billion years ago. In those earliest instants, the universe was remarkably smooth and uniform. Matter and energy were distributed almost evenly throughout space. But not quite evenly. There were tiny variations in density, fluctuations of only a few parts per 100,000. These variations were quantum fluctuations from the very earliest moments of the universe, stretched to cosmic scales by a brief period of exponential expansion called cosmic inflation. These tiny density variations were the seeds of everything that would come later. Regions that were slightly denser than average had slightly stronger gravity. This stronger gravity attracted more matter from the surrounding space. As more matter accumulated, the gravity became stronger still, attracting even more matter in a runaway process. Meanwhile, regions that were slightly less dense than average had weaker gravity. Matter in these regions was pulled toward the denser regions, making the underdense areas even emptier over time. This process of gravitational instability operated over billions of years. The denser regions collapsed under their own gravity, forming the first stars, galaxies, and eventually clusters of galaxies. The underdense regions, meanwhile, became voids, expanding as matter drained away toward the filaments and nodes. The process creates a characteristic pattern, with matter flowing from voids into filaments, and from filaments into clusters, like water flowing through a network of rivers toward the ocean. But there's another crucial player in this story, one that doesn't emit or absorb light and therefore remained unknown to astronomers for most of human history. Dark matter makes up approximately 85% of all matter in the universe. Unlike the ordinary matter that forms stars, planets, and people, dark matter interacts only through gravity. It doesn't emit, absorb, or reflect electromagnetic radiation, making it invisible to telescopes. We know it exists because we can see its gravitational effects on visible matter and on the path of light traveling through space. Dark matter played the dominant role in creating the cosmic web. Because it doesn't interact with light or radiation, it could begin clumping together earlier and more efficiently than ordinary matter. In the early universe, ordinary matter was still being buffeted by radiation pressure, prevented from collapsing by the intense bath of photons that filled space. But dark matter was already collecting in halos, forming the gravitational scaffolding along which ordinary matter would later flow. Computer simulations that track the evolution of millions of dark matter particles through billions of years of cosmic history beautifully reproduce the web-like structure we observe. These simulations show dark matter collecting along filaments, with the densest concentrations at the intersections where multiple filaments meet. The voids appear as regions where dark matter is sparse, but not entirely absent. Even in the deepest voids, there's still some dark matter, along with tenuous filaments of dark matter that thread through the void's interior like ghostly echoes of the larger cosmic web. The voids themselves have structure. They're not perfect spheres or simple bubbles. Many are elongated or irregular in shape. Some appear to be made up of multiple smaller voids that have merged together over time. The boundaries between voids and filaments aren't sharp walls, but rather gradual transitions where the density of matter increases. At the very edges of voids, where they meet the surrounding filaments, matter can pile up in relatively dense walls or sheets. Understanding void formation requires grappling with another mysterious component of the universe: dark energy. In 1998, astronomers made a startling discovery. They found that the expansion of the universe isn't slowing down due to gravity, as everyone had expected. Instead, it's accelerating. Something is pushing space apart, counteracting gravity on the largest scales. This something has been dubbed dark energy, and it makes up approximately 68% of the total energy content of the universe. Dark energy affects how voids evolve. In a universe without dark energy, voids would eventually stop expanding and might even begin to collapse as matter on their edges pulls inward. But in our universe, dominated by dark energy, voids continue to grow. The acceleration of cosmic expansion means that the filaments surrounding voids are being pulled apart, and the voids themselves are getting larger over time. In the distant future, billions of years from now, this process will continue until individual galaxy clusters become isolated from one another, each surrounded by ever-expanding voids. The voids we observe today are shaped by this complex interplay of gravity, dark matter, and dark energy. They're laboratories for studying fundamental physics, regions where the effects of dark energy can be measured and where the properties of dark matter can be inferred from the distribution of the few galaxies that do exist within them. The formation process itself is worth examining in more detail. In the very early universe, moments after the Big Bang, quantum fluctuations created tiny ripples in the fabric of space-time. These ripples represented regions where the density of matter was slightly higher or slightly lower than average. The differences were minuscule, just a few parts per 100,000, but they were enough to set the stage for everything that would follow. As the universe expanded and cooled, these density fluctuations began to grow. In regions that were slightly denser than average, gravity worked to pull in even more matter, making them denser still. The process was gradual at first. For hundreds of millions of years, the fluctuations remained small. But gravity is patient and relentless. Every time a slightly denser region pulled in a bit more matter, its gravitational field became slightly stronger, allowing it to pull in even more matter. The feedback was positive, amplifying the initial tiny differences into increasingly dramatic contrasts. Meanwhile, in regions that started out slightly less dense than average, the opposite occurred. These regions had slightly weaker gravitational fields than their surroundings. Matter within them was preferentially pulled toward the denser neighboring regions. As matter flowed out, the gravitational field became weaker still, allowing even more matter to escape. These underdense regions were the seeds of future voids. The process accelerated over time. By the time the universe was a few 100 million years old, the first stars were forming in the densest regions. By 1 billion years, the first galaxies had assembled. By several billion years, Galaxy clusters and superclusters had formed, and the cosmic web's structure was becoming apparent. All the while, the voids were expanding, growing larger and emptier as matter drained toward the filaments and nodes. But the story doesn't end there. The voids themselves have a life cycle. Young voids in the early universe were smaller and contained more matter than voids today. Over cosmic time, voids have grown. Small voids have merged to form larger ones. The Boötes Void, with its tube-like structure of galaxies running through its center, likely formed from several smaller voids coalescing. When voids meet and merge, the galaxies that had been on their boundaries can end up threading through the interior of the merged void, creating exactly the kind of structure we observe. The expansion of voids isn't uniform across their volumes. At a void's center, where the matter density is lowest, the expansion can proceed quite rapidly. Near the edges, where matter density increases as you approach the surrounding filaments, the expansion is slower. This creates a density profile for voids, with the emptiest regions at their centers and a gradual increase in density toward their boundaries. Many voids show a characteristic bucket shape to their density profiles, with a relatively flat, low-density interior surrounded by a steeper density increase at the edges where matter has accumulated in shells or ridges. Scientists have developed sophisticated algorithms to identify and characterize voids in galaxy surveys. These algorithms must account for the fact that voids aren't simple geometric shapes but complex, evolving structures. Different methods of void finding can produce somewhat different results, which is why cosmologists carefully compare multiple approaches to ensure they're measuring real physical structures rather than artifacts of their analysis techniques. The study of voids has revealed that they come in a hierarchy of sizes. Small voids might be only 30 million light-years across. Medium-sized voids can span 100 million light-years or more. And then there are the supervoids, enormous underdense regions like the Boötes Void that stretch for hundreds of millions of light-years. These supervoids are defined not just by their size but by the absence of rich superclusters of galaxies within them. They represent the most extreme examples of cosmic emptiness. What's particularly fascinating is that voids appear to evolve in predictable ways. Young voids in the early universe were smaller and less empty than voids today. Over time, as matter has continued to flow out of underdense regions and into filaments, voids have grown larger and more empty. This evolution provides a way to test our cosmological models by comparing the number and size distribution of voids at different cosmic epochs. Astronomers can check whether the universe is evolving in the way our theories predict. The Boötes Void, a closer look at the Great Nothing. Now let's return to the Boötes Void and examine it in more detail. This remarkable structure has been studied extensively since its discovery, and each new observation has added layers to our understanding of what makes it so unusual. The void is roughly spherical, though not perfectly so. Its center lies approximately 700 million light-years away from Earth in the direction of the constellation Boötes, the herdsman. In ancient mythology, Boötes was the figure who drove the celestial plow, represented by the Big Dipper eternally around the pole star. It's a fitting location for a discovery that plows through our assumptions about cosmic structure. With a radius of about 162 million light-years, the Boötes Void would take light more than 300 million years to cross from edge to edge. The void's volume is staggering. If we were to calculate how much space it occupies, we'd be dealing with numbers that have little meaning in everyday terms. Suffice it to say that you could fit millions of regions the size of our local galactic neighborhood within the Boötes Void. What makes this void so striking is its galaxy density, or rather, the lack thereof. Astronomers have found approximately 60 galaxies within the void, though the exact number depends somewhat on how you define the void's boundaries and what counts as a galaxy versus a smaller dwarf galaxy that might be difficult to detect. Some estimates put the number closer to 30, while deep observations with sensitive instruments have pushed the count higher, perhaps to a few hundred if you include very faint dwarf galaxies. Even taking the higher estimates, this is an extraordinarily low number. In a typical region of space this size, you would expect to find around 2,000 galaxies, perhaps more. The Boötes Void contains less than 10% of the expected galaxy population. In terms of matter density, the ES void is estimated to have only about 10 to the power of -5 galaxies per cubic megaparsec, compared to the cosmic average of about 0.01 galaxies per cubic megaparsec. A megaparsec, for reference, is roughly 3.26 million light-years. The galaxies that do exist within the void aren't randomly distributed. They tend to cluster along a tubular region that runs through the center of the void. This tube-like structure has led some researchers to propose that the Boötes Void formed from the merger of several smaller voids. As smaller voids expanded and their edges met, they would have merged into a single, larger void, with the galaxies along the boundary between the original voids forming the filament we now observe. The few galaxies within the Boötes Void appear to have some unusual properties compared to galaxies in denser regions. Many of them are relatively small, faint dwarf galaxies. They tend to have active star formation, producing new stars at rates that are high for their mass. Some show spectroscopic signatures of young stellar populations with lots of hot, blue stars. This suggests that void galaxies might be evolving differently from their counterparts in more crowded regions. One particularly interesting resident of the Boötes Void is a dwarf galaxy catalogued as ESO 461-36, which was studied intensively to understand void dynamics. This little galaxy appears to be moving away from the void's center at a velocity of about 216 kilometers per second, roughly 134 miles per second. This outward motion is exactly what we'd expect if the void is an underdense region. The galaxy is being gravitationally pulled toward the denser walls surrounding the void, like a marble rolling toward the edge of a bowl. By studying the motion of galaxies like this, astronomers can infer properties of the void itself. The faster a galaxy is moving outward, the stronger the density. Contrast between the void's interior and its surroundings must be. These measurements help constrain models of void evolution, and can even provide information about the nature of dark energy, since dark energy affects how rapidly voids expand. The Boötes Void is surrounded by several major superclusters of galaxies. These include the Ursa Major supercluster, the Shapley supercluster, the Hercules supercluster, the Corona Borealis supercluster, and the Boötes supercluster itself. These massive collections of galaxy clusters form the walls and filaments that bound the void, creating a striking contrast between the densely populated regions and the nearly empty interior. What can we learn from studying a structure like the Boötes Void? First, it provides a crucial test of our cosmological models. The standard model of cosmology, known as lambda cold dark matter, or lambda CDM, makes specific predictions about how structure should form in the universe. It predicts that voids of various Sizes should exist, and it even predicts roughly how many voids of each size we should see. The existence of the Boötes Void is consistent with these predictions. While it's a large void, it's not so large that it contradicts the standard model. However, voids also provide opportunities to look for deviations from the standard model. If we found voids that were significantly larger or emptier than the lambda CDM model allows, that would suggest something was wrong with our understanding of cosmology. So far, the Boötes Void and other known voids fall within the expected range, but astronomers continue to search for potential anomalies. Second, the Boötes Void helps us understand the role of environment in galaxy evolution. Galaxies don't evolve in isolation. They're influenced by their surroundings, by interactions with other galaxies, by the density of gas in intergalactic space, and by the overall gravitational environment they inhabit. Void galaxies, like those in the Boötes Void, offer a chance to study galaxy evolution in the most pristine, isolated environments in the universe. By comparing void galaxies to galaxies in clusters and filaments, we can tease apart which aspects of galaxy evolution are intrinsic to the galaxies themselves, and which are shaped by environmental factors. Third, study in voids can reveal information about dark matter and dark energy. The distribution of dark matter in and around voids affects how galaxies move, and how light from distant objects is bent as it passes through these regions. By carefully mapping these effects, astronomers can infer properties of the dark matter distribution. Similarly, the rate at which voids expand provides information about dark energy's properties and how it affects cosmic expansion. The Boötes Void has been the subject of numerous observational campaigns using telescopes across the electromagnetic spectrum. Radio telescopes have mapped the distribution of neutral hydrogen gas within the void. X-ray telescopes have searched for hot intergalactic gas. Optical telescopes continue to hunt for faint galaxies that previous surveys might have missed. Each observation adds detail to our picture of this remarkable structure. In recent years, sophisticated surveys like the Sloan Digital Sky Survey have provided unprecedented detail about the three-dimensional structure of the cosmic web, including voids. These surveys measure the positions and redshifts of millions of galaxies, allowing astronomers to create detailed maps showing how matter is distributed across billions of light-years. The Boötes Void appears in these maps as a striking gap in the galaxy distribution, a bubble in the cosmic foam. Despite decades of study, the Boötes Void continues to hold mysteries. We still don't fully understand why this particular void is so large and so empty. Was it just a statistical fluctuation, a region where the initial density perturbations in the early universe happened to be particularly low, or did some other process contribute to its formation? These questions remain open areas of research. What we can say with certainty is that the Boötes Void represents one of the most extreme examples of cosmic structure we've discovered. It challenges us to understand how something so vast can be so empty, and in doing so, it teaches us about the fundamental forces and components that shape our universe, the KBC Supervoid, living in the cosmic desert. While the Boötes Void is remarkable for its size and emptiness, there's another void that hits closer to home, literally. Our own Milky Way galaxy, along with our local group of galaxies and even our larger cosmic neighborhood, appears to reside within or on the edge of an enormous underdense region known as the KBC Void, also called the local hole. This supervoid is named after the three astronomers who characterized it in 2013, Ryan Keenan, Amy Barger, and Lennox Cowie. The KBC void is immense. Estimates of its size vary depending on exactly how you measure it and define its boundaries, but most studies suggest it spans approximately 2 billion light-years in diameter, or about 600 megaparsecs. That makes it one of the largest known voids in the observable universe. Some analyses suggest it might be even larger, potentially approaching 3 billion light-years across in certain directions. What makes the KBC void particularly intriguing is that it's not a traditional void in the sense of being almost completely empty. Instead, it's what astronomers call an underdensity. The region contains galaxies, including our own Milky Way, the local group of galaxies, and the larger Laniakea supercluster, to which our local group belongs. But the overall density of matter in this region is lower than the cosmic average. Estimates suggest the KBC void is about 15 to 50% less dense than typical regions of the universe, with most studies converging on a value around 20% underdense. This might not sound like much. 20% less dense doesn't seem as dramatic as the Boötes Void's near total emptiness. But when you're talking about a region 2 billion light-years across, even a 20% deficit in matter density represents an enormous amount of missing mass. The gravitational effects of this underdensity can influence the motion of galaxies across vast distances and potentially affect our observations of cosmic expansion. The discovery and characterization of the KBC void has been the subject of debate in the astronomical community. Some researchers question whether such a large underdensity is consistent with the standard lambda-CDM model of cosmology. The model predicts that the universe should be relatively homogeneous on the largest scales, with matter distributed fairly evenly when averaged over sufficiently large volumes. A void 2 billion light-years across with a 20% density deficit strains this assumption of homogeneity. Several studies have analyzed galaxy number counts in different directions across the sky, looking at how the density of galaxies changes with distance. These analyses have found evidence supporting the existence of a local underdensity extending out to about 1 billion light-years from us. The underdensity appears to be roughly spherical, with our position somewhat off-center within it, perhaps a few 100 million light-years from the void's true center. Other research has approached the question differently, using observations of the cosmic microwave background and measurements of the local expansion rate. These studies have also found hints that we might reside in an underdense region, though the exact size and depth of the underdensity remains uncertain. If the KBC void is real, it has profound implications. For one, it affects how we should interpret observations made from our position within it. When we look out at the universe, we're looking from within this underdense region. The lower matter density around us means that the local gravitational field is weaker than it would be in an average region of the universe. This can affect the motion of nearby galaxies and the rate at which space appears to be expanding in our cosmic neighborhood. This brings us to one of the most perplexing problems in modern cosmology: the Hubble tension. The Hubble constant, denoted h0, is a number that describes the current rate of expansion of the universe. Knowing this number precisely is crucial for understanding the universe's age, size, and ultimate fate. But here's the problem. Different methods of measuring the Hubble constant give different answers, and the disagreement is significant enough that it can't be easily explained by measurement uncertainties. One method uses observations of the cosmic microwave background, the afterglow of the Big Bang. These measurements, combined with the standard cosmological model, predict a Hubble constant of about 67 to 68 kilometers per second per megaparsec. This means that for every megaparsec of distance, space is expanding at about 67 to 68 kilometers per second. Another method uses observations of relatively nearby galaxies and supernovae, measuring distances and recession velocities directly. These local measurements consistently give a higher value, around 72 to 75 kilometers per second per megaparsec. The difference might seem small, but it's statistically significant. Both sets of measurements have been refined and checked numerous times, and the discrepancy persists. This is where the KBC void enters the picture. If we're located in a significant underdensity, it could affect our local measurements of the Hubble constant. Here's how. In an underdense region, there's less matter to gravitationally slow down the expansion of space. Meanwhile, the denser matter surrounding the void pulls outward on galaxies within it. The combined effect is that galaxies in and near the void would have an additional outward velocity component beyond what's caused by the universe's overall expansion. When we measure the recession velocities of nearby galaxies, we'd be measuring this boosted expansion rate, making it appear that the universe is expanding faster locally than it actually is on average. Several research groups have proposed that if the KBC void is large enough and underdense enough, this effect could potentially explain the discrepancy between local and cosmic microwave background measurements of the Hubble constant. The idea is elegant, but it faces challenges. For the void to fully resolve the Hubble tension, it would need to be quite large and quite underdense, potentially more so than some analyses suggest it actually is. Additionally, the standard lambda CDM model has difficulty explaining how such a large void could have formed in the first place. The model includes specific predictions about the sizes and depths of voids that should exist, and the KBC void, if it's as large and deep as some studies suggest, would be pushing the boundaries of what the model allows. Some researchers have proposed that the tension could be resolved if we modify our theory of gravity. Modified Newtonian dynamics, or MOND, is an alternative to the dark matter hypothesis that proposes gravity behaves differently than Einstein's general relativity predicts, especially in weak gravitational fields like those found in the outskirts of galaxies and in cosmic voids. In MOND, the KBC void could be larger and deeper than lambda CDM allows, potentially explaining both the Hubble tension and some observations of galaxy rotation curves that currently require dark matter to explain. However, MOND faces its own challenges and hasn't gained widespread acceptance in the cosmology community. Most researchers still work within the framework of general relativity and lambda CDM, while acknowledging that the Hubble tension remains an unsolved problem that might point to new physics. The Milky Way's location within or near the KBC void affects more than just expansion measurements. Our galaxy's motion through space is influenced by the gravity of surrounding matter. Astronomers have identified several components to the Milky Way's motion. We're being pulled toward the Virgo cluster at about 185 kilometers per second. We're also being pulled toward a more distant concentration of mass called the Great Attractor at about 455 kilometers per second. And there's a repulsive component, a motion away from the local void at approximately 260 kilometers per second. This outward motion from the void combines with the attractive motions toward overdense regions to give our galaxy its overall trajectory through space. The existence of the KBC void if confirmed and better understood, would represent a significant feature of our local universe. It would mean that when we observe the cosmos, we need to account for the fact that we're viewing it from an unusual vantage point, somewhat like living in a valley and trying to understand the geography of a mountain range. Our local observations would be colored by our local environment. Recent studies using baryon acoustic oscillations, a feature in the distribution of galaxies that serves as a standard ruler for measuring cosmic distances, have provided additional evidence for a local underdensity. These studies suggest that a void model is vastly more likely than a model without a void when trying to explain certain observational data. However, other analyses using different data sets and methods have reached less definitive conclusions, highlighting the ongoing nature of the research. What's clear is that the question of whether we live in a supervoid is more than an academic curiosity. It touches on fundamental questions about the universe's structure, the nature of cosmic expansion, and how we should interpret observations made from our particular location in space. As surveys continue to map the distribution of galaxies across ever larger volumes of the universe, and as measurements of the Hubble constant continue to be refined, we'll gain a clearer picture of whether the KBC void is the missing piece needed to solve one of cosmology's biggest puzzles, the Eridanus supervoid and the cosmic microwave background cold spot. Among all the voids discovered by astronomers, few have generated as much scientific interest and debate as the Eridanus supervoid. This enormous underdense region, located in the constellation Eridanus in the southern celestial hemisphere, might hold the key to understanding one of the most puzzling features ever discovered in the cosmic microwave background. The cosmic microwave background, or CMB, is the oldest light in the universe. It's the afterglow of the Big Bang itself, radiation that has been traveling through space for more than 13 billion years. When we observe the CMB, we're looking back to a time when the universe was only about 380,000 years old, long before the first stars or galaxies had formed. At that early epoch, the universe was filled with a hot, dense plasma. As the universe expanded and cooled, the plasma eventually became transparent, releasing the radiation we now detect as the CMB. The CMB is remarkably uniform. Its average temperature is about 2.7 Kelvin, which is 2.7 degrees above absolute zero. But the CMB isn't perfectly uniform. It contains tiny fluctuations in temperature, variations of only about 1 part in 100,000. These fluctuations represent the seeds of all future structure, the density variations that would eventually grow into galaxies and clusters. Studying the pattern of these fluctuations has provided cosmologists with invaluable information about the early universe, the geometry of space, and the composition of cosmic matter and energy. In 2004, data from NASA's Wilkinson Microwave Anisotropy Probe, known as WMAP, revealed something unusual. In a region of the sky toward the constellation Eridanus, there was a cold spot, an area where the CMB temperature was notably lower than the surrounding regions. The cold spot was big, subtending an angle of about 5 degrees on the eye's sky, roughly 10 times the apparent diameter of the full moon. At its coldest point, the temperature was about 70 microkelvins, or 0.00007 Kelvin, colder than the average CMB temperature. Some parts of the cold spot were as much as 140 microkelvins colder than average. Now, 70 to 140 microkelvins might not sound like much, but in the context of the CMB's tiny temperature fluctuations, it's significant. The root mean square of typical temperature variations in the CMB is only about 18 microkelvins. The cold spot is several times larger and colder than what you'd typically expect from the primordial fluctuations that seeded cosmic structure. When astronomers calculated the probability of such a large, cold feature arising purely from the quantum fluctuations in the early universe that produced the CMB's temperature pattern, they found it was unlikely but not impossible. The probability was estimated at about 1.85%. This is unusual enough to merit attention, but not so unusual that it definitively points to something beyond the standard model of cosmology. It could just be a statistical fluke, a rare but not impossible configuration of the primordial fluctuations. Various explanations were proposed for the cold spot. Some suggested it might be a signature of exotic physics from the very early universe, perhaps evidence of a cosmic texture left over from a phase transition shortly after the Big Bang, or even, in some speculative proposals, the imprint of another universe beyond our own through quantum entanglement at cosmic scales. But there was another, more prosaic possibility: a foreground void. If a large void existed between us and the surface of last scattering, the spherical shell from which the CMB photons we observe were emitted, that void could create a cold spot through what's known as the integrated Sachs-Wolf effect. The Sachs-Wolf effect is a phenomenon where photons from the CMB gain or lose energy as they travel through changing gravitational potentials. Photons climbing out of a gravitational potential lose energy, becoming red-shifted and cooler. Photons falling into a potential gain energy, becoming blue-shifted and hotter. In a static universe, these effects would cancel out perfectly as photons enter and then leave a void. But in an expanding universe dominated by dark energy, the cancellation isn't perfect. Here's what happens. CMB photons enter a void, a region with lower matter density and therefore a shallower gravitational potential. As they enter, they gain a bit of energy from falling into the potential. They cross the void. As they exit, they lose energy climbing out. But because the universe is expanding and dark energy is stretching space, the void grows larger and shallower while the photons are crossing it. When they exit, the potential well isn't as deep as it was when they entered. The energy they lose on exit is less than the energy they gained on entry. The net result is that the photons leave the void with less energy than they had, appearing colder. This integrated Sachs-Wolf effect is stronger for larger voids and in a universe with more dark energy. It provides a way for foreground structures to imprint signatures on the CMB we observe. If the cold spot was caused by a void through this mechanism, it would need to be a very large void, a supervoid. In 2015, a team of astronomers led by Istvan Zapudi announced the discovery of the Eridanus supervoid. Using galaxy survey data, they identified a significant underdensity of galaxies in the direction of the CMB cold spot. The supervoid appeared to be centered about 2 billion light-years away from us, with the underdensity extending from us out to about 3 billion light-years. The void was estimated to be about 1.8 billion light-years in diameter, making it one of the largest structures known. More importantly, it was located almost perfectly aligned with the CMB cold spot. The discovery was exciting, but it raised as many questions as it answered. Could a void this size, located at this distance, actually explain the cold spot? Theoretical calculations suggested that the integrated Sachs-Wolf effect from such a void should produce a temperature depression of only about 20 microkelvins in the CMB. The actual cold spot is more than 7 times colder. reaching depths of 140 microkelvins or more in its central regions. This created a puzzle. The Eridanus supervoid appeared to be real. It was aligned with the cold spot, but it seemed insufficient to fully explain the temperature anomaly. Perhaps the cold spot was partly due to the supervoid and partly due to primordial fluctuations. Or perhaps our understanding of the integrated Sachs-Wolf effect was incomplete. Subsequent studies have refined our picture of the Eridanus supervoid. In 2021, researchers using data from the Dark Energy Survey confirmed the void's existence using gravitational lensing. Gravitational lensing is a technique where the bending of light by gravity is used to map the distribution of matter, including dark matter. The team created a map of dark matter in the region of the cold spot and found a clear underdensity, confirming that the Eridanus supervoid exists in the dark matter distribution as well as in the galaxy distribution. The Dark Energy Survey data revealed that the Eridanus supervoid is about 20 to 30% less dense than the cosmic average and extends across roughly 1.8 billion light-years. It appears as the most prominent large-scale underdensity in the entire Dark Energy Survey dataset, which covers a substantial fraction of the southern sky. This confirmed that the supervoid is indeed a major structure, not just a minor fluctuation in the galaxy distribution. However, the study also found something puzzling. The amplitude of the gravitational lensing signal from the Eridanus supervoid was about 30% weaker than expected, based on simulations using the standard lambda CDM model. This could mean that the void is shallower than theoretical models predict, or it could hint at something unusual about how the void formed or evolved. If the void's lensing signal is weaker than expected, it might actually help explain the cold spot. A shallower void could mean that it was deeper in the past, when CMB photons were passing through it. A void that has become shallower over time would have produced a stronger integrated Sachs-Wolf effect than we'd calculate based on its current depth. This could potentially bring the predicted temperature depression closer to the observed value. Alternatively, the weaker lensing signal might indicate that the standard cosmological model isn't quite right. Perhaps dark energy behaves slightly differently than we think, or perhaps the way structure grows in the universe deviates from lambda CDM predictions in ways we haven't accounted for. If true, this would be a significant discovery, suggesting that even our best cosmological models need refinement. Other research has compared the temperature signature of the Eridanus supervoid to supervoids elsewhere in the sky, and found a pattern. Multiple studies have reported that large supervoids, those formed from the merging of several smaller voids, produce integrated Sachs-Wolf signals that are stronger than the standard lambda CDM model predicts. These observed signals can be about 5 times stronger than the model expects. This suggests something systematic might be going on, some aspect of how supervoids interact with the CMB that our current models don't fully capture. The debate over the cold spot and its relation to the Eridanus supervoid continues. Some researchers argue that the supervoid can explain a significant fraction of the cold spot, perhaps 10 to 20%, with the rest being due to primordial fluctuations. Others suggest that if we account for the uncertainties in void evolution and the integrated Sachs-Wolf effect, the supervoid might explain even more of the anomaly. What's not in doubt is that the Eridanus supervoid exists, and that it coincides with the CMB cold spot. Whether this coincidence is causal or just a cosmic accident remains an open question. The supervoid provides a plausible physical mechanism that could contribute to the cold spot. But pinning down exactly how much it contributes requires better understanding of void evolution, the integrated Sachs-Wolf effect in the presence of dark energy, and the statistical properties of the CMB's primordial fluctuations. Future observations will help resolve these questions. Deeper galaxy surveys will map the three-dimensional structure of the Eridanus supervoid in greater detail. More sensitive CMB observations will refine the temperature map of the cold spot. Improved computer simulations will better predict the integrated Sachs-Wolf signatures of large voids in different cosmological models. All of this work will converge on a clearer picture of whether the cold spot is a window into exotic early universe physics, a product of foreground structure, or most likely some combination of both. Life inside a void, the peculiar galaxies of emptiness. While cosmic voids are defined by their lack of galaxies compared to the cosmic average, they're not completely empty. The galaxies that do exist within voids offer a unique opportunity to study galaxy formation and evolution in the most isolated, pristine environments in the universe. These void galaxies, as they're called, appear to have properties that set them apart from their counterparts in denser regions, providing insights into how environment shapes galaxy development. One of the most striking features of void galaxy populations is their color distribution. When astronomers examine the light from galaxies, they classify them as either blue or red based on their overall color. Blue galaxies are actively forming stars. The hot, massive, short-lived stars that dominate young stellar populations emit most of their light at blue wavelengths, giving these galaxies their characteristic hue. Red galaxies, by contrast, have largely ceased forming new stars. Their stellar populations are dominated by older, cooler stars that emit more light at red wavelengths. In the general galaxy population across the universe, you find a mix of blue star-forming galaxies and red quiescent galaxies. But in voids, the balance shifts. Studies have consistently found that voids contain a higher proportion of blue star-forming galaxies compared to galaxies in walls, filaments, and clusters. This excess of blue galaxies in voids appears to be a robust feature, confirmed by multiple surveys using different void-finding algorithms and different galaxy samples. At first glance, this might seem puzzling. You might expect that the pristine, low-density environment of voids would make it harder for galaxies to form stars. After all, star formation requires gas, and in voids there's less of everything, including gas. But the actual picture is more nuanced. It turns out that the excess of blue galaxies in voids is partly, perhaps largely, a mass effect. Void galaxies tend to be less massive than galaxies in denser environments. When you look at galaxies of the same stellar mass, many of the differences between void and non-void galaxies diminish or disappear. The color distributions of blue galaxies in voids versus blue galaxies elsewhere, when controlled for mass, are remarkably similar. The same is true for red galaxies. What this suggests is that voids don't fundamentally change how galaxies form stars at a given mass. Instead, voids preferentially host lower-mass galaxies, and lower-mass galaxies are more likely to be blue and star-forming regardless of where they live. But this raises another question. Why do voids host more low-mass galaxies? The answer relates to how galaxies form and grow. Galaxies form within dark matter halos, invisible cocoons of dark matter that provide the gravitational potential wells where gas can collect and condense to form stars. The mass of a galaxy is closely related to the mass of its dark matter halo, more massive halos host more massive galaxies. In voids, the typical dark matter halo mass is lower than in denser regions. This makes sense given the definition of voids as underdense regions. With less dark matter overall, you have fewer massive halos and more low-mass halos. Consequently, you get more low-mass galaxies. These low-mass galaxies tend to be blue and star-forming, giving voids their characteristic excess of blue galaxies. But there's more to the story. When astronomers look at specific star formation rates, the rate of star formation divided by the galaxy's stellar mass, they find that void galaxies often have higher specific star formation rates than comparable galaxies in denser environments. This means that while void galaxies are forming stars, they're doing so at a rate that's high relative to their mass. They're actively building up their stellar populations. Studies of void galaxy spectra, the rainbow of light broken down by wavelength, reveal high equivalent widths for emission lines associated with star formation. Emission lines like hydrogen alpha, oxygen doubly ionized, and others that trace hot, ionized gas in star-forming regions are particularly strong in void galaxies. This confirms that these galaxies are experiencing vigorous star formation. The metallicity of void galaxies, the abundance of elements heavier than hydrogen and helium, also appears to be distinctive. Several studies have found that void galaxies tend to have lower gas metallicity compared to galaxies of similar mass in denser regions. However, this finding is somewhat controversial, with some studies finding significant differences and others finding none. The metallicity of stars in void galaxies, the stellar metallicity, also shows interesting patterns, with some evidence that void galaxies are slightly less metal-rich in their stars. Lower metallicity would make sense if void galaxies are less evolved. In the universe, metals are produced by stars through nuclear fusion. When stars explode as supernovae or shed their outer layers at the end of their lives, these metals are returned to the interstellar medium, enriching the gas from which future generations of stars will form. Galaxies that have experienced multiple generations of star formation will be more metal-rich. If void galaxies are younger or have formed fewer generations of stars, they'd be expected to have lower metallicity. The morphology of void galaxies, their structure and shape, is another area of study. Galaxies are broadly classified into two morphological types: spirals, with their characteristic pinwheel structure and active star formation in spiral arms, and ellipticals, which are smooth, round, or elliptical in shape with little ongoing star formation. There are also irregular galaxies and various intermediate types. Several studies have examined the morphological mix of void galaxies. Some have found that void galaxies are more likely to be late-type spirals and irregulars, consistent with their blue colors and active star formation. Others have found that when you control for stellar mass, the morphological distributions of void and non-void galaxies are similar. The picture that emerges is that voids don't radically change galaxy morphology at a given mass, but they do shift the mass distribution toward lower masses, and lower mass galaxies are more likely to have late-type morphologies. One fascinating aspect of void galaxy evolution is the role of mergers. In dense environments like galaxy clusters, mergers between galaxies are common. When two galaxies collide and merge, the interaction can trigger bursts of star formation, redistribute gas and stars, and ultimately transform spiral galaxies into elliptical ones. In voids, mergers are much rarer simply because galaxies are farther apart. A void galaxy might go billions of years without experiencing a significant interaction with another galaxy. This isolation means that void galaxies evolve in a fundamentally different way than cluster galaxies. They grow primarily through what astronomers call secular evolution, slow processes driven by the galaxy's own internal dynamics rather than by dramatic interactions. They accrete gas from their surroundings, form stars from that gas, and gradually build up their stellar populations. Without mergers to redistribute their gas and trigger intense starbursts, void galaxies can maintain steady, moderate rates of star formation over long timescales. This makes void galaxies valuable as laboratories for understanding galaxy evolution. By studying how galaxies evolve in the absence of mergers and dense environmental effects, astronomers can better understand which aspects of galaxy evolution are intrinsic to the galaxies themselves and which are environmentally driven. Computer simulations of galaxy formation have proven invaluable for interpreting observations of void galaxies. Modern cosmological simulations track the evolution of millions of dark matter particles and gas parcels through billions of years of cosmic history. They include sophisticated models of star formation, supernova feedback, black hole growth, and other physical processes that shape galaxy evolution. These simulations can identify void regions in their simulated universes and examine the properties of galaxies that form there. The simulated void galaxies show many of the same trends as observed ones. They tend to be less massive, bluer, more star-forming, and morphologically later type. The simulations reveal that void galaxies experience less merging, accrete gas more gradually, and evolve more slowly than their counterparts in denser regions. One particularly interesting finding from simulations is that void galaxies tend to have higher gas fractions, meaning a larger proportion of their baryonic mass is in the form of gas rather than stars. This makes sense given their active star formation and lower stellar masses. They haven't yet converted as much of their gas into stars as more evolved galaxies have. The simulations also show that the relationship between galaxies and their dark matter halos is somewhat different in voids. For a given dark matter halo mass, void galaxies tend to have slightly lower stellar masses. This suggests that galaxy formation is somewhat less efficient in voids, perhaps because the lower density environment makes it harder for halos to accrete gas, or perhaps because feedback from star formation and supernovae more easily expels gas from the shallow potential wells of the lower mass halos typical of voids. Perhaps most intriguingly, void galaxies represent some of the most pristine examples of galaxies in the universe. They're the cosmic equivalent of isolated islands, removed from the major currents of cosmic structure. They've likely formed from nearly pure intergalactic gas, without the complex assembly histories involving multiple mergers that characterize many galaxies in denser regions. Studying them offers a window into what galaxy formation looked like in its simplest, most fundamental form. As surveys continue to improve and as we push observations to fainter galaxies, our census of void galaxies will continue to grow. Each new void galaxy discovered adds to our understanding of how galaxies form and evolve in the universe's emptiest regions. And each puzzle they present, each way they deviate from or conform to our expectations, teaches us something new about the processes that shape all galaxies, whether they live in voids or in clusters, in filaments or in walls, dark matter, dark energy, and the contents of cosmic emptiness. When we describe cosmic voids as empty, we're speaking in relative terms. Compared to the dense filaments and clusters that make up the cosmic web's skeleton, voids are indeed nearly devoid of galaxies. But they're not empty in an absolute sense. Understanding what actually exists within voids reveals fundamental truths about the composition of the universe itself. Let's start with dark matter. We know that approximately 85% of all matter in the universe is dark matter. This mysterious substance interacts only through gravity, making it invisible to telescopes but detectable through its gravitational influence on visible matter and light. Dark matter provides the gravitational scaffolding for all cosmic structure, from individual galaxies to the largest filaments and voids. In voids, dark matter is sparse but not entirely absent. Computer simulations that track the evolution of dark matter through cosmic history show that void regions contain wispy filaments and tendrils of dark matter, like faint echoes of the grander cosmic web that surrounds them. These dark matter structures within voids are much less dense than the filaments that bound the voids, but they're not non-existent. The presence of dark matter within voids has been inferred in several ways. Gravitational lensing studies, which measure how the path of light is bent by gravity, can detect concentrations of matter including dark matter. While these studies are challenging in voids due to the low density, they've confirmed that dark matter exists there, forming a faint web-like structure even in the most underdense regions. The average density of matter, both dark and ordinary, in the deepest parts of voids, is estimated to be about 15% of the cosmic average, or about 100 times less than the cosmic average in the very deepest regions. This means that while voids are certainly underdense, they still contain a significant fraction of the universe's matter when you consider their enormous volume. In terms of ordinary matter, the stuff that makes up stars, planets, and people, voids contain even less than the cosmic average. Most ordinary matter in the universe isn't found in stars and galaxies anyway. It exists as diffuse gas in intergalactic space, heated to temperatures of millions of degrees in some regions. In voids, this intergalactic gas is particularly tenuous. The average density of ordinary matter in the deepest parts of voids might be only a few atoms per cubic meter. To put that in perspective, the best vacuum we can create in laboratories on Earth is nowhere near that empty. Laboratory vacuums might contain millions of atoms per cubic meter. The depths of cosmic voids are emptier by far, approaching the limit of emptiness possible in our universe. Yet, even in these near-perfect vacuums, you can still find traces of matter. There might be an occasional hydrogen atom drifting through space. There might be extremely faint dwarf galaxies, too dim for most surveys to detect. There might be dark matter halos that failed to collect enough ordinary matter to form visible galaxies. The voids are emptier than almost anywhere else, but they're not absolute vacuums. Now, let's consider another component: radiation. Even the emptiest voids are bathed in radiation, particularly the cosmic microwave background. This ancient light, the afterglow of the Big Bang, fills every cubic centimeter of the universe. It has a temperature of about 2.7 Kelvin, just above absolute zero, and it's redshifted into microwave wavelengths by the expansion of the universe. The cosmic microwave background represents the most abundant form of radiation in the universe. No matter where you are, in the densest cluster or the emptiest void, you cannot escape it. It's truly universal. However, the energy density of the cosmic microwave background is very low. Its photons are so deeply redshifted that they carry almost no energy individually. So, while the radiation is omnipresent, it contributes very little to the total energy content of voids. There are other sources of radiation in voids as well. Starlight from galaxies, though sparse, adds a faint background glow. High-energy cosmic rays, charged particles accelerated to nearly the speed of light, traverse voids just as they traverse denser regions. Neutrinos, merely massless particles that rarely interact with anything, stream through voids in vast numbers. All of these contribute to the radiation field in voids, but none contributes significantly to the void's energy density. Which brings us to the most important component of cosmic voids, dark energy. Dark energy is the mysterious force or field responsible for the accelerating expansion of the universe. It makes up approximately 68% of the total energy density of the cosmos. Unlike matter and radiation, which become diluted as the universe expands, dark energy appears to have a constant density. As space expands, more dark energy comes into existence to maintain the same energy density per unit volume. In dense regions like galaxy clusters, dark energy is present, but its effects are overwhelmed by the gravity of the matter there. Gravity dominates on these scales, holding clusters together and even pulling in more matter from the surroundings. But in voids, where matter is sparse and gravity is weak, dark energy takes over. Voids are the domains where dark energy's influence is most pronounced. The expansion of space within voids is driven primarily by dark energy. While the universe as a whole is expanding, voids are expanding even faster than average. The low density of matter within them means there's little gravitational pull to resist the expansion driven by dark energy. As a result, voids grow over time, becoming larger and emptier as matter continues to flow out of them toward the denser filaments and clusters. This makes voids crucial laboratories for studying dark energy. By measuring how rapidly voids expand, by studying how their sizes and depths evolve over cosmic time, and by examining how they affect the motion of galaxies within and around them, astronomers can constrain the properties of dark energy. Different models of dark energy predict slightly different behaviors for void evolution, so detailed observations of voids can help discriminate between these models. One particularly important property is the equation of state of dark energy, usually denoted W. This parameter describes the relationship between dark energy's pressure and its density. The simplest model, often called the cosmological constant, predicts W equals -1. More complex models of dark energy, sometimes called quintessence, predict values of W that might differ from -1 and might even change over time. Voids are sensitive to the value of W. The shape of voids, their rate of expansion, and the way matter flows around them all depend on dark energy's properties. By carefully comparing observations of voids to predictions from models with different values of W, cosmologists can constrain dark energy's equation of state. This is one of the key goals of modern observational cosmology. Another aspect of voids that provides cosmological information is their abundance. The standard lambda CDM model makes specific predictions about how many voids of each size should exist in the universe. If we observe significantly more or fewer voids than predicted, or if we find voids that are larger or deeper than the model allows, that would suggest something is wrong with the model. Perhaps dark energy behaves differently than we think, or perhaps our understanding of structure formation needs revision. So far, observations of void abundances and sizes have been generally consistent with lambda CDM predictions. The Boötes Void, while large, is not so large that it contradicts the model. The KBC void, if it exists at the size some studies suggest, pushes the boundaries but might still be accommodated. The Eridanus supervoid falls within the expected range. But astronomers continue to search for potential outliers, for voids that might reveal deviations from the standard model. Voids also provide information about neutrinos, the ghostly particles that rarely interact with anything. Neutrinos have a very small but non-zero mass, and they can affect structure formation on large scales. In particular, neutrinos can stream freely in and out of voids that are smaller than the neutrino mean free path. This affects the size distribution of voids and their internal structure. By comparing observed voids to models with different neutrino masses, astronomers hope to measure the total mass of all neutrino species, a quantity that's difficult to determine through other means. In a very real sense, voids are filled with dark energy. While we often think of voids as empty spaces between the material structures of the universe, they're actually vast reservoirs of dark energy, the dominant component of cosmic energy density. Dark energy may be invisible and intangible, but it's doing real work in voids, stretching space, driving expansion, and shaping the evolution of cosmic structure. This realization changes how we should think about voids. They're not just gaps in the cosmic web. They're active participants in cosmic evolution, regions where dark energy's influence is paramount, where the expansion of the universe is most rapid, and where the ultimate fate of our cosmos is being written in the gradual expansion and emptying of these vast regions. The Hubble tension and the role of voids. One of the most perplexing problems in modern cosmology, one that has resisted numerous attempts at resolution, is the Hubble tension. This seemingly technical issue strikes at the heart of our understanding of the universe's expansion, its age, and the fundamental physics that govern cosmic evolution. And, intriguingly, cosmic voids might play a crucial role in solving this mystery. The Hubble constant, denoted as h0, is a number that quantifies the current rate of expansion of the universe. Its name honors Edwin Hubble, who in the 1920s discovered that the universe is expanding. The Hubble constant tells us how fast space is stretching. Specifically, it describes how much faster galaxies are receding from us for each additional unit of distance. The standard units are kilometers per second per megaparsec, meaning that for every megaparsec of distance from us, galaxies are moving away an additional so many kilometers per second, due to cosmic expansion. Measuring the Hubble constant precisely has been a goal of cosmology for decades. It's not just an academic exercise. The Hubble constant is intimately connected to the age of the universe, its size, its matter and energy content, and its ultimate fate. Knowing h0 precisely allows us to determine whether the universe is 13.8 billion years old or 14.2 billion years old. It affects our estimates of when the first stars formed. It influences our understanding of dark energy's strength. In short, it's a fundamental number in cosmology. For many years, different methods of measuring the Hubble constant gave roughly consistent results, with uncertainties large enough that any disagreements could be attributed to measurement errors. But as measurements have improved and uncertainties have shrunk, a troubling discrepancy has emerged. One approach to measuring h0 uses the cosmic microwave background. Detailed maps of the CMBs, temperature fluctuations, combined with the standard lambda CDM model of cosmology, allow us to infer the Hubble constant. The logic is complex, involving the physics of the early universe, the geometry of space, and the evolution of cosmic expansion, but the method is robust and has been refined over years of careful work. The most precise CMB-based measurements from the Planck satellite give a Hubble constant of about 67.4 kilometers per second per megaparsec, with an uncertainty of only about half a kilometer per second per megaparsec. Another approach uses what's called the cosmic distance ladder. This method starts with nearby objects whose distances can be measured geometrically without assuming anything about cosmic expansion. From these nearby calibrators, astronomers build up a ladder of distance measurements extending to galaxies hundreds of millions of light-years away. At each rung of the ladder, one type of object calibrates the next. Cepheid, variable stars, which pulsate with periods that depend on their luminosity, serve as crucial middle rungs. Type 1 supernovae, which are believed to have a standard peak luminosity, serve as the bright endpoints visible across vast distances. By measuring the distances to galaxies hosting these supernovae and comparing those distances to the galaxy's recession velocities, astronomers can determine the Hubble constant. The most precise distance ladder measurements, led by teams using the Hubble Space Telescope and other facilities, give a Hubble constant of about 73.0 kilometers per second per megaparsec, with an uncertainty of about 1 kilometer per second per megaparsec. The difference between 67.4 and 73.0 might seem small, but it's highly significant. The two measurements disagree by more than 5 sigma, meaning the probability of the discrepancy arising from random chance is less than 1 in a million. This isn't just a matter of better measurements revealing a small difference. It's a genuine tension that suggests something is wrong either with our measurements or with our understanding of cosmic expansion. Numerous attempts have been made to resolve the Hubble tension. Perhaps there are systematic errors in the distance ladder measurements. Maybe the calibrations of Cepheid variables or Type 1 supernovae aren't as reliable as we think. Or perhaps the CMB-based measurements are affected by some unaccounted for foreground emission, or by deviations from the standard cosmological model in the early universe. Researchers have scrutinized both sets of measurements exhaustively, looking for errors or biases, but the tension persists. This is where cosmic voids enter the picture. If we live in a significant underdensity, a large supervoid like the KBC void, it could affect our local measurements of the Hubble constant without affecting the CMB-based measurements. Here's the mechanism. In an underdense region, there's less matter to gravitationally slow down cosmic expansion. Additionally, the denser matter surrounding the void pulls outward on it, creating flows of matter away from the void's center. Galaxies in and near the void acquire additional peculiar velocities, motions beyond the simple expansion of space. When we measure the recession velocities of relatively nearby galaxies, as is done in the distance ladder approach, we're measuring the combination of true cosmic expansion plus these peculiar velocities. If the peculiar velocities systematically point away from us because we're in a void, the measured recession velocities will be higher than they would be in an average region of the universe. This makes it appear that the local expansion rate is faster than the cosmic average. Crucially, this effect would only influence local measurements. The CMB-based measurements probe the expansion rate averaged over the entire observable universe, not just our local neighborhood. They wouldn't be affected by our residing in a void. So a void could potentially create exactly the kind of discrepancy we observe. local measurements giving a higher Hubble constant than global measurements. Several research groups have explored whether the KBC void could explain the Hubble tension. The calculations require estimating the void's size, depth, and our location within it. Then, computing how these factors affect the motion of galaxies in our vicinity. The results are promising, but not definitive. For the void to fully resolve the Hubble tension, it would need to be quite substantial. Studies suggest it would need to extend out to about 1 billion light-years or more, with a density deficit of around 20% compared to the cosmic average. Some observational analyses find evidence for exactly such a void. Others find a smaller or less pronounced underdensity that can only partially explain the tension. One challenge is that the standard lambda CDM model has difficulty accommodating a void as large and deep as would be needed. The model includes specific predictions about the statistical properties of cosmic structure, including how large the largest voids should be. A 2 billion light-year void that's 20% underdense pushes against the limits of what lambda CDM predicts, though it's not definitively ruled out. This has led some researchers to consider whether the Hubble tension might be pointing toward new physics. Perhaps the lambda CDM model needs modification. Maybe dark energy behaves differently than we think, or maybe gravity itself deviates from general relativity in ways that become apparent only on the largest scales or in the weakest gravitational fields. Modified Newtonian dynamics, or MOND, is one alternative that's been proposed. In MOND, gravity behaves differently from what Newton and Einstein predicted in regimes of extremely weak acceleration. This altered gravity could allow for larger, deeper voids than lambda CDM permits. If MOND is correct, the KBC void could be sufficiently large to explain the Hubble tension while also potentially explaining other observations, like the rotation curves of galaxies, without requiring dark matter. However, MOND faces significant challenges. It has difficulty explaining observations on cluster scales, where dark matter appears necessary. It doesn't naturally accommodate the cosmic microwave background's detailed structure. Most cosmologists remain skeptical of MOND, preferring to work within the framework of general relativity and dark matter while acknowledging that the Hubble tension remains an unsolved problem. Recent work has provided additional tests of the void hypothesis. If we're in a void that's causing the Hubble tension, that should create other observable effects. For instance, it should affect the cosmic bulk flow, the large-scale motion of galaxies in our cosmic neighborhood. Surveys that measure galaxy velocities across large volumes can test whether the observed bulk flows are consistent with what we'd expect from a void. Some studies have found evidence for bulk flows that are larger than expected in the standard model, potentially supporting the void hypothesis. Others have found results more consistent with standard predictions. The situation remains unsettled. Another approach involves measuring the Hubble constant at different distances. If we're in a void, the local Hubble constant should appear high when measured with nearby galaxies, but should decrease as we look to more distant galaxies outside the void. Some research has claimed to detect exactly this trend, with measurements at 200 million light-years giving higher values than measurements at 1 billion light-years. However, these results are not universally accepted, and other studies have reached different conclusions. The void solution to the Hubble tension has the appeal of potentially killing two birds with one stone. It could explain both why local and global measurements disagree, and why we observe evidence for a local underdensity in galaxy counts. But it requires us to accept that we live in a rather special location in the universe, in one of its largest and deepest voids. This raises questions about the Copernican principle, the idea that we don't occupy a special place in the cosmos. Of course, someone has to live in the large voids. Voids occupy most of the universe's volume, so, in a statistical sense, we're more likely to be in a void than in a dense filament. But not all voids are large enough and deep enough to explain the Hubble tension. Whether it's likely or unlikely that we'd find ourselves in exactly the kind of void needed depends on how common such voids are, which brings us back to questions about cosmological models and structure formation. The Hubble tension remains one of the most active areas of research in cosmology. Each new survey that maps galaxy distributions, each new measurement of the Hubble constant using different methods, and each new analysis of the CMB or of large-scale structure contributes to our understanding. Voids are unlikely to be the entire story, but they may well be part of it. Resolving the tension will probably require a combination of better measurements, better understanding of systematic errors, and possibly new physics that extends or modifies the lambda CDM model. What's clear is that cosmic voids, once thought to be merely empty spaces between the interesting structures, have emerged as potentially crucial players in some of cosmology's deepest mysteries. The future of void research. Mysteries remaining. As we've explored cosmic voids in detail, a picture has emerged of structures that are far more complex and important than simple empty regions. They're laboratories for fundamental physics, probes of dark energy, windows into galaxy evolution, and possibly keys to solving cosmological puzzles. Yet, for all we've learned, many mysteries remain. One of the most fundamental questions is simply, what exactly are the boundaries of voids? Where does a void end and a filament begin? Different void-finding algorithms can produce somewhat different answers. Some methods identify voids based on underdensities in galaxy counts. Others use the underlying dark matter distribution inferred from simulations or gravitational lensing. Still others define voids based on the flow of matter, looking for regions where material is escaping outward. Each approach has merits, but they don't always agree precisely on where void boundaries lie. This might seem like a technical detail, but it affects everything we try to learn from voids. If we're measuring the size distribution of voids to constrain dark energy, we need to know where one void ends and another begins. If we're studying void galaxy properties, we need to know which galaxies are truly inside voids, and which are in the transition regions between voids and filaments. Developing more robust, physically motivated definitions of voids remains an ongoing area of research. Another mystery concerns void evolution. We understand the broad outlines. Voids start as slightly underdense regions in the early universe and grow over time as matter flows out of them. But the details matter. How do voids merge when they meet? What determines which voids grow to become supervoids, and which remain small? How is the internal structure of voids, the faint filaments of dark matter that thread through them, affected by the surrounding cosmic web? Computer simulations can address these questions, but simulations have limitations. They require choices about which physical processes to include and how to model them. They have finite resolution, meaning they can't capture the smallest structures, and they rely on our current understanding of cosmology, which might need refinement. Comparing simulations to observations of real voids can reveal discrepancies that point toward needed improvements in our models. The role of voids in galaxy evolution also holds open questions. We know void galaxies tend to be bluer, more star-forming and less massive than galaxies in denser regions. But are these differences purely due to the mass distribution, or do voids affect galaxies more directly? Some studies suggest that galaxy formation is less efficient in voids, meaning that for a given dark matter halo mass, void galaxies have lower stellar masses. If true, this implies that the environment affects fundamental aspects of how gas cools, forms stars, and is retained or expelled from galaxies. Understanding these environmental effects could have broader implications. It could help us interpret observations of distant galaxies in the early universe, which formed in environments quite different from the present-day cosmic web. It could inform our models of how supermassive black holes grow, since the availability of gas and the frequency of mergers both differ between voids and clusters. Voids provide a kind of controlled experiment, allowing us to isolate environmental factors in galaxy evolution. The connection between voids and the cosmic microwave background is another rich area for future work. We've discussed the Eridanus supervoid and the cold spot, but there are other supervoids and other features in the CMB that might be related. By systematically comparing the locations of large voids to the temperature pattern of the CMB, accounting for the integrated Sachs-Wolf effect, astronomers can test our understanding of how foreground structures imprint themselves on the CMB we observe. If we find that the observed correlations between voids and CMB features are stronger or weaker than predicted, that would tell us something important. Perhaps the integrated Sachs-Wolf effect works differently than we think, or perhaps our catalogs of voids are missing some structures or falsely identifying others. Either way, we'd learn something new. Upcoming surveys promise to revolutionize our understanding of voids. The Euclid satellite, launched by the European Space Agency, is designed to map the distribution of galaxies across billions of light-years with unprecedented precision. It will use both direct galaxy counts and weak gravitational lensing to create three-dimensional maps of both ordinary and dark matter. These maps will reveal voids in exquisite detail, allowing astronomers to study their shapes, sizes, and internal structures as never before. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct the legacy survey of space and time, photographing the entire visible sky every few nights for 10 years. This survey will discover and characterize countless new voids, track how their galaxies evolve, and possibly reveal rare, extreme voids that could challenge cosmological models. Future CMB missions, building on the legacy of WMAP and Planck, will map the microwave sky with even greater sensitivity and resolution. Combined with galaxy surveys, these observations will allow detailed studies of how voids affect the CMB through the integrated Sachs-Wolf effect and other mechanisms. They might even reveal correlations too subtle to detect with current data. These future observations will work in concert with advances in theoretical understanding. Cosmologists are developing increasingly sophisticated models of void formation and evolution, incorporating better physics for gas cooling, star formation, and feedback from supernova and black holes. Machine learning algorithms are being trained to identify voids automatically in vast datasets, potentially finding subtle features that human researchers might miss. One particularly exciting frontier is the study of void environments across cosmic time. By looking at distant galaxies and ancient voids from billions of years ago, we can watch how void properties have evolved over the history of the universe. Do voids in the early universe follow the same patterns as voids today? Have they grown in the ways our models predict? These questions can only be answered by pushing observations to greater distances and earlier times. The interplay between voids and the intergalactic medium, the gas that fills the space between galaxies, is another area ripe for exploration. This diffuse gas is extremely tenuous but not entirely negligible. It can be traced through its absorption of light from distant quasars, creating what astronomers call the Lyman alpha forest in quasar spectra. By studying how this forest changes when lines of sight pass through voids versus filaments, we can learn about the temperature, density, and ionization state of gas in different environments. This, in turn, tells us about the radiation field that pervades the universe and about how gas flows through the cosmic web. Magnetic fields in voids represent another mystery. Observations have detected weak magnetic fields throughout intergalactic space, but their origin remains unclear. Were they generated in the very early universe through some primordial process? Or were they created later, perhaps by outflows from galaxies or by other astrophysical mechanisms? Voids, with their pristine environments relatively untouched by galaxy-driven processes, might preserve clues to the origin of cosmic magnetism. Studies of how gamma rays from distant blazars are deflected as they traverse voids could reveal the strength and structure of void magnetic fields. The relationship between voids and cosmic rays, high-energy particles that stream through space, is largely unexplored. Cosmic rays are thought to be accelerated in supernovae, active galactic nuclei, and other energetic environments. As they propagate through space, they interact with magnetic fields and radiation. Do cosmic rays behave differently in voids compared to denser regions? Can we use cosmic ray observations to probe void environments? These questions await answers from future experiments. Perhaps most intriguingly, voids offer a potential testing ground for alternative theories of gravity. In modified gravity theories like MOND, the behavior of matter in weak gravitational fields differs from what general relativity predicts. Voids, with their low densities and weak gravity, are exactly where such deviations might become apparent. By carefully studying how galaxies move within voids, how voids expand, and how their properties compare to standard model predictions, we can test whether general relativity holds up in these extreme environments. The future may also bring surprises. Astronomy has a history of unexpected discoveries that overturn our understanding. Perhaps we'll find voids that are larger or emptier than should be possible. Perhaps we'll detect signals in voids from exotic physics, like decaying dark matter particles, or interactions between dark energy and dark matter. Perhaps we'll discover that voids play a role in cosmic magnetism, seeding the magnetic fields that permeate space. What seems certain is that voids will continue to be important in cosmology. They're not just empty spaces to be ignored while we focus on galaxies and clusters. They're fundamental components of cosmic structure, shaped by the same physics that governs everything else, and they hold information about the universe's composition, evolution, and ultimate fate. As you drift toward sleep, perhaps you can imagine what it would be like to journey through a cosmic void. You'd leave behind the familiar sight of our Milky Way and the nearby galaxies that dot our cosmic neighborhood. As you traveled outward, the density of galaxies would thin. The bright lights of stars and galaxies would become sparser, more isolated. Eventually, you'd enter the void itself, a region so vast that you might travel for 100 million light-years in any direction and encounter only a handful of dim dwarf galaxies. The darkness would be profound, but not absolute. The cosmic microwave background would still bathe you in its faint glow. Distant galaxies at the void's edges would shine like a faint halo on the horizon in every direction. And all around you, invisible but ever present, dark energy would be gently pushing space apart, expanding the void, making the emptiness even more empty. It's a humbling vision, a reminder of the universe's immense scale and the variety of environments it contains. From the densest galaxy clusters to the emptiest voids, from the hot, bright centers of stars to the cold, dark depths of intergalactic space. The cosmos encompasses everything. And we, from our small planet orbiting an average star in an average galaxy, have learned to map it, understand it, and find our place within it. Conclusion. As we come to the end of our journey through cosmic voids, let yourself sink deeper into comfort. Your breathing has slowed, become more regular. The weight of your body presses gently into the surface beneath you. The concerns of the day have faded, replaced by thoughts of vast cosmic spaces and the patient work of understanding them. We've traveled from the discovery of the Boötes Void in 1981 to the cutting edge of modern cosmology. We've explored how voids form from tiny quantum fluctuations in the early universe, amplified over billions of years by the interplay of gravity, dark matter, and dark energy. We've seen how these enormous empty regions shape the cosmic web, how they host unusual galaxies evolving in isolation, and how they might hold keys to some of cosmology's deepest mysteries. The voids teach us humility. We live in a universe where 80% of the volume is nearly empty space. Vast regions, hundreds of millions of light years across, where galaxies are rare and matter is sparse. These voids dwarf anything we can easily comprehend. They remind us that the universe operates on scales far beyond human experience. Yet they also inspire wonder. Even in the emptiest regions of space, we find structure, evolution, and information. The voids aren't just nothing. They're shaped by fundamental forces. They contain dark energy in its purest form. They host galaxies that tell stories of cosmic isolation and pristine evolution. They affect the cosmic microwave background, leaving subtle signatures we can detect and study. And, perhaps most remarkably, we've learned to study them. With our telescopes and our satellites, our computer simulations and our mathematical models, we've mapped these enormous structures. We've measured their sizes, cataloged their galaxies, inferred their dark matter content, and used them to probe the nature of dark energy. Human ingenuity and curiosity have reached out across hundreds of millions of light years to understand what shapes the universe's emptiest places. As you drift toward sleep, carry with you the image of a cosmic void. An enormous bubble in space, almost empty, but not quite. Faint tendrils of dark matter threading through the darkness. Rare, isolated galaxies glowing dimly in the vastness. Dark energy gently pushing everything apart. It's a peaceful image, a place of cosmic calm where the universe expands in near silence and time passes on scales we can barely imagine. Nothing about these cosmic holes is normal by our everyday standards. They're too big, too empty, too strange. But they're fundamental to the universe we inhabit. They shape the cosmic web. They test our theories. They host unique environments for galaxy evolution. They might even explain why our measurements of cosmic expansion don't agree. Let these thoughts wash over you like gentle waves. The universe is vast beyond comprehension, yet we understand it. It's strange beyond imagination, yet we can map it. It's ancient beyond our ability to truly grasp, yet we've learned its history. And in all that vastness, all that strangeness, all that time, there's a place for curiosity, for wonder, for the human drive to understand. Rest now. Dream of cosmic voids and distant galaxies, of dark energy and expanding space, of mysteries solved and mysteries remaining. The universe will still be there tomorrow, waiting to be explored, its voids patiently expanding, its secrets gradually yielding to our persistent questions. Sleep well,